Assalamualaikum warahmatullahi wabarakatuh. Today my friend and I from group 5 will present about lab 3, which is state space representation.
For calculation in part A, by using nodal analysis method to the circuit, we can obtain the equation of VI minus VL equal to VC1. From the equation, it can be obtained VL equal to VI minus VC1 and then convert VL to the derivative equation, that is L DIL per dt, to get the equation for DIL per dt. From the circuit, it can get the equation VL equal to VR plus VC2 because the voltage value for parallel is equal to its opposite. Then it can obtain the equation for IC2R equal to VL plus VC2 and then convert IC2 to the derivative equation, that is CdVC2 per dt, to obtain the equation of dVC2 per dt. By using nodal analysis method as well, it can get the equation IC1 equal to IL plus IC2. Then convert IC1 and IC2 to the derivative equation of CdVC per dt and find the equation for dVC per dt. By using the derivative equation obtained, it can be written in vector matrix form. Because the output voltage is at capacitor 2, the voltage of the capacitor 2 will be 1.
Hi, my name is Elia and I will present to you about coding in part A. First, we declare all the value of R, C1, C2 and L to 1. Then, this is the state space equation that we get and we declare the state space. Next, this is the numerator and denominator for matrix A, B, C and D. The answer that has been obtained from matrix A, B, C and D was used to find transfer function. The transfer function that we get is this. The transfer function that we get is this. For the output response that has been obtained is stable and declining until the steady state response equal to 0. For simulating, first we put an integrator, then we put gain A and gain B. After that, we put sum block to perform addition for input of gain A and gain B. We put unit step at gain B. Next, we put gain C and scope to find the output. The output that we obtain from the simulating is unit step response plot. This is the output response for unit step response after running the simulating. This is the comparison of the unit step response using MATLAB command and using simulating. The step response unit using simulating was a delay on the graph plot because it does not start off 0 compared to the step response unit using MATLAB command that start with 0.
Hi, my name is IZZATI. Now I will explain to you part B, conservation state space to transfer function. First, we need to obtain the state space representation from part A, and then we calculate the value for Si minus A. Si is the identity of S and minus with matrix A. Then we get this matrix. Then we replace R, C1, C2 and L with 1. Then this is the final matrix that we get for Si minus A. After that, we calculate the inverse for Si minus A. To get an inverse Si minus A, use formula adjoint Si minus A over determinant Si minus A. This is the matrix that we get for inverse Si minus A. To get the transfer function, we use formula GS equal to C inverse SI minus A, B plus D. So this is the metric of C, this is the metric of SI minus A, and this is metric B. First, we multiply matrix C with SI inverse SI minus A, and then we get this metric. After that, this metric we multiply with metric B. So this is the final equation that we get for transfer function. GS is equal to S squared over S cubed plus 2S squared plus S plus 1. Now I will explain to you the MATLAB of part B. First, we initialize the value of R, C1, C2 and L. Then we use command sim_s to declare S parameter. After that, we declare the state variable of A, B, C and D according to the state space that we get from part A. Then we use command SI equal to S times I3 to determine the identity of S. So we put 3 inside the bracket because the matrix of A has dimension of 3 times 3 matrix. So this is that we get for SI, which is S is in diagonal position. After that, we calculate the value for SI minus A, because we use command SIA is equal to SI minus A, and then this is the value that we get for SI minus A on the command window. After that, we calculate the value for inverse SI minus A. So we use command inverse SIA. Then this is the value for inverse SI minus A that we get on the command window. To obtain the transfer function, we use command G is equal to C times SI A inverse times B plus D. Then we get the transfer function. This transfer function is a complex equation. To simplify the transfer function, we add simplify command on the transfer function command. So we get this more simpler or more simplified transfer function, and then we get S power of 2 over S power of 3 plus 2S power of 2 plus S plus 1. To plot the unit step response, first we declare the numerator and the denominator, and then we use command SYS is equal to TF bracket num comma. Then because we want to get the transfer function from the numerator and denominator that we have declared before, and then we use command step bracket SYS to plot the unit step response. This is the output of the unit step response. As you can see, the step response that we get from this system is a stable step response. On 0.892 seconds, the system reached its peak response with the amplitude of 0.353. And then at 50 seconds, the system reached its steady state response with the amplitude of 0.
That's all from us. Thank you.